Here's something that sounds like a confession. After centuries of telescopes and brilliant minds, the honest truth is that scientists do not know what most of the universe is made of, not a small corner of it. Most of it, the ordinary matter that makes up you and the stars and everything you have ever touched, adds up to only a few percent of all that exists. The rest is a mystery with a name, but no face. And that is only the beginning of what we cannot explain. Tonight we wander slowly through the greatest unsolved puzzles of the cosmos, the questions that keep astronomers quietly awake. Before we begin, I would love to know which town or city you are drifting off in tonight and what the hands of your clock are showing right now. Leave it below if you like. Now let us slow everything down. There is no destination tonight. That is worth saying clearly because we are going to spend the next while in the company of unanswered questions, and unanswered questions can make the restless mind lean forward, wanting resolution. Tonight we are going to do the opposite. We are going to lean back. Each of these mysteries has been sitting patiently in the universe for billions of years, and not one of them needs solving before morning. So you can let each one wash over you like a slow tide and then recede without holding on to it. You do not need to follow the whole map. You do not need to remember a single fact. If you fall asleep somewhere in the middle of the missing antimatter or drift off among the radio bursts from the far side of the sky, that is not a failure. That is exactly what these quiet, enormous questions are for tonight. They are here to give your mind something vast and calm to rest against. So let us begin the way people have always begun, with the universe, by looking up. Imagine for a moment that you are lying on your back somewhere far from city lights on a cool, clear night, with the whole sky spread open above you. At first it looks simple, a scattering of stars, a few brighter than the rest, the pale band of the Milky Way arching overhead. For most of human history, that was the whole picture, a dome of lights that turned slowly through the night. It looked complete, it looked knowable, and there is a deep and understandable comfort in that feeling, the sense that the sky is a finished thing, a ceiling of stars hung once and left alone. But the closer we have looked, the stranger it has become. Every time we built a better instrument or listened in a new way, the tidy picture cracked open a little further, and behind the crack was something we did not expect and could not yet explain. The universe, it turns out, is not a finished painting. It is more like a vast, dim room that we are exploring by candlelight, and every few steps the candle reveals something that makes us stop and wonder how much more is out there in the dark. Tonight we are going to visit some of those half-lit shapes at the edge of the candlelight. Not to solve them, just to sit with them slowly, one at a time, and feel the enormous, gentle strangeness of the cosmos we happen to live inside. And the first one is hiding, of all places, in the way the galaxies turn. Think about a spinning thing you know well, a record on a turntable, or the swirl of coffee in a mug after you stir it, or the water circling a drain. In all of these, there is a simple rule that your body already understands. The parts near the center move around quickly, and the parts near the edge move more slowly. Our own solar system obeys this rule beautifully. Mercury, close to the sun, races around its orbit in just 88 days. Neptune, far out in the cold, takes almost 165 years to complete a single loop. The farther a planet is from the sun's gravity, the more leisurely its journey. This is one of the oldest and most reliable patterns in all of astronomy. worked out from the laws that Isaac Newton wrote down in the 1680s. The gravity holding you in orbit weakens with distance, so the outer things move slower. It is as dependable as anything in science. So when astronomers first turned their attention to how galaxies spin, they expected the very same pattern. A galaxy like our Milky Way is a great disk of hundreds of billions of stars, turning slowly in space, with a bright, crowded bulge of stars at its center where most of the visible matter seems to be. By the logic of the solar system, the stars near that bright center should whirl around quickly, and the stars way out at the faint edges, far from all that central mass, should drift around much more slowly. That was the confident prediction. The outer stars should lag behind. And it was here in the late 1960s and early 1970s that a careful American astronomer began to notice that the galaxies were not reading from the same script. Her name was Vera Rubin, born in 1928, and she was one of those quietly persistent scientists who changed everything not with a single dramatic flash, but with patient, meticulous measurement. Working with a gifted instrument builder named Kent Ford, who had developed a very sensitive tool for measuring the motion of starlight, Rubin set out to measure how fast the stars were orbiting at different distances from the center of the great neighboring galaxy of Andromeda, and then in galaxy after galaxy beyond it. She was measuring the speed of the outer stars, expecting to watch those speeds fall away with distance, just as Neptune moves slower than Mercury. What she found instead was one of the strangest and most important results in the history of astronomy. The outer stars were not slowing down. Out at the far edges of the galaxies, where there was almost no visible matter left, where by every expectation the orbits should have been sluggish and slow, the stars were racing around just as quickly as the stars much closer in. The speed simply refused to drop off. If you drew a graph of orbital speed against distance from the center, a graph astronomers call a rotation curve, it did not slope gently downward the way the solar systems would. It ran out flat, almost level, stretching far beyond the visible edge of the galaxy, as though nothing were changing at all. And that flatness, that stubborn refusal of the outer stars to slow down, is a genuine crisis dressed up as a simple line on a graph. Here's why it matters so much. The speed at which a star can orbit is set by the gravity pulling on it, and gravity is set by mass. For those far-out stars to be moving so fast without being flung off into intergalactic space entirely, there had to be far more mass tugging on them than anyone could see, a great deal more. The visible stars and gas simply did not add up to enough gravity to hold those speedy outer stars in their orbits. It was as though you watched a stone whirling on the end of a string, moving far too fast for the thin thread you could see, and were forced to conclude that there must be a much stronger, invisible rope doing the real work of holding it in. And so astronomers were pushed, reluctantly, toward an extraordinary conclusion. There must be enormous amounts of matter in and around every galaxy that we simply cannot see. Matter that gives off no light, no radio waves, no glow of any kind, that neither shines nor blocks the light behind it, but that has mass and therefore gravity. And that gravity is holding the galaxies together. They called it dark matter, and the name is really just an honest label for our ignorance. It does not mean the matter is black or shadowy. It means it is invisible to us. Dark in the sense of hidden, felt only through its gravitational pull on the things we can see. The idea had actually been glimpsed decades earlier, though the world was not ready to listen. Back in 1933, a brilliant and famously prickly Swiss-American astronomer named Fritz Zwicky, born in 1898, had studied a great swarm of galaxies called the Coma Cluster and noticed that the galaxies within it were moving far too fast to be held together by the visible matter alone. By his calculation, the cluster should have flown apart long ago unless something unseen was holding it together with extra gravity. He coined a term for this missing mass, which in German was dunkle Materie, dark matter. But his results sat quietly in the literature for 40 years, a curiosity few knew what to do with, until Rubin and Ford's careful measurements of ordinary spinning galaxies made it impossible to ignore any longer. The dark matter was not a quirk of one strange cluster. It was everywhere, wrapped around every galaxy in a vast, invisible halo. Now here is the part that should make you feel the true weight of the mystery. When astronomers add it all up, this unseen dark matter is not a minor ingredient sprinkled around the edges. There appears to be roughly 5 or 6 times more dark matter in the universe than all the ordinary matter of stars and planets and gas and people combined. The galaxies we admire, all their glittering stars, are like a little bright froth riding on top of a vast invisible ocean of something else. The universe we can see is the exception. The universe we cannot see is the rule. And to this day, after decades of searching, no one knows what the dark matter actually is. It is not for lack of trying. Physicists have built exquisitely sensitive detectors and buried them deep underground, in old mines and beneath mountains, shielded from all the ordinary radiation of the world, hoping to catch the faint, rare nudge of a dark matter particle drifting through. They have proposed candidates with names like weakly interacting massive particles and axions, and many others, whole families of hypothetical particles that would have mass and gravity but would otherwise slip through ordinary matter like a ghost through a wall, almost never touching anything. Trillions of them may be passing through your body as you lie here, silent and untouched. And yet, in all these years, not one of these detectors has caught a confirmed, undisputed dark matter particle. We can map where it is by watching how it bends starlight and holds galaxies together. We can weigh it. We can trace its invisible presence across the whole sky. But we cannot say what it is. It remains the largest, nearest, and most patient mystery of all, wrapped invisibly around the very galaxy you live in, felt in the turning of every distant star, and still, after all this time, entirely unknown. Let us drift now to a different kind of mystery, one that is not about something hidden in the dark, but about a disagreement between two very careful measurements of the same simple-sounding number, a disagreement so stubborn and so persistent that it has come to be called attention. To feel why it matters, we first have to sit for a moment with one of the most astonishing facts ever discovered about the universe, which is that it is not standing still. It is growing. For most of history, people assumed the universe was fixed and eternal, the stars hanging in their places forever. The first cracks in that assumption came from a quiet woman working at Harvard College Observatory in the early 1900s named Henrietta Swan Leavitt, born in 1868. Leavitt was employed as what they then called a computer, one of a group of women paid to carefully examine photographic plates of the night sky and catalog the brightness of stars. It was painstaking, underappreciated work, and out of it she drew a discovery that would unlock the scale of the entire cosmos. Studying a certain kind of pulsing star, a type that brightens and dims in a steady rhythm called a Cepheid variable, she noticed a beautiful and reliable pattern. The slower a cepheid pulsed, the brighter it truly was. And that meant that if you timed a cepheid's rhythm, you could know its real brightness, and by comparing that to how dim it appeared in the sky, you could work out how far away it was. She had found a cosmic measuring stick, a way to gauge the distances to faraway stars. Armed with that measuring stick, astronomers began to map the universe, and the map kept getting bigger. In the 1920s, using Leavitt's method, they realized that the faint smudges of light they had thought were clouds of gas within our own galaxy were in fact entire other galaxies, island universes of billions of stars, unimaginably far away. And then came the truly staggering part. An American astronomer named Edwin Hubble, born in 1889, working with the Great Telescope on Mount Wilson in California, measured not only the distances to these galaxies, but also the way their light was stretched. And he found that almost every galaxy was moving away from us, and, crucially, that the farther away a galaxy was, the faster it was receding. A Belgian priest and physicist named Georges Lemaitre, born in 1894, had in fact worked out much the same thing a couple of years earlier and understood its meaning deeply. The galaxies were not flying away through space so much as being carried apart by space itself, which was expanding, swelling, stretching in every direction like the surface of a balloon, being slowly blown up, with every galaxy, a dot on that balloon, drifting away from every other. This gave astronomers a number to chase, one of the most important numbers in all of science. It describes how fast the universe is expanding, how quickly those galaxies are being carried apart, and it is named in Hubble's honor the Hubble constant. You can think of it loosely as the current growth rate of the cosmos. Pin down that number precisely, and you can wind the expansion backward to learn the age of the universe and forward to glimpse its fate. And so, for the better part of a century, measuring the Hubble constant as accurately as possible has been one of the central quests of astronomy, which brings us at last to the tension. There are two great ways to measure how fast the universe is expanding, and here is the heart of the puzzle. They should agree. They are two paths to the same single number, the growth rate of one universe, and they do not agree. They have not agreed for years. And no matter how carefully astronomers refine each method, hunting for some hidden mistake, the gap between them stubbornly refuses to close. The first way is the direct local method, a modern descendant of Leavitt's measuring stick. Astronomers, in recent years, led by a team under the astronomer Adam Rees, born in 1969, patiently build what they call a distance ladder. They start with those trusty pulsing Cepheid stars, whose distances they can measure well and use them to calibrate a brighter beacon, a particular kind of exploding star called a Type Ia supernova, which flares up with a very predictable brightness and can be seen across enormous distances. Rung by rung, star by supernova, they measure out into the far reaches of the expanding universe, and from how fast those distant galaxies are receding, they calculate the expansion rate directly. This local, present-day method gives a value of roughly 73 in the particular units astronomers use, kilometers per second for every megaparsec of distance. The exact units do not matter tonight. What matters is the number, about 73. The second way is entirely different, and it comes from the deep past. Astronomers study the faint afterglow of the Big Bang itself, an ancient light we will meet again later tonight, which carries within it a detailed snapshot of the infant universe. Using the exquisite measurements of that ancient light gathered by a European spacecraft called the Planck satellite, and applying our best understanding of the physics of the early cosmos, they can predict how fast the universe ought to be expanding today. This early universe method, reading the growth rate from the seeds of the cosmos rather than from the galaxies around us, gives a different number. It gives roughly 67, 73 from one method, 67 from the other. And you might think at first that these numbers are close enough that surely a little difference like that is nothing to lose sleep over. But that is exactly the point that makes astronomers so uneasy. Both measurements have become so extraordinarily precise, their possible errors whittled down so finely, that the gap between them is now far too large to be brushed aside as ordinary uncertainty. Each measurement on its own is quite sure of itself, and yet they disagree. It is as though two people measured the same table with two very good rulers, and one kept getting a meter, and the other kept getting 9/10 of a meter, and no amount of remeasuring would bring them together. Something somewhere is not what we think it is, and that is what makes the Hubble tension so quietly thrilling and so unsettling to the people who study it. If both measurements are right, and they each look right, then the flaw is not in the measuring. The flaw is in our understanding of the universe between the two, in the long story that connects the infant cosmos to the galaxies of today. It could mean there is some new ingredient we have missed, some early form of dark energy, some new kind of particle, some subtle piece of physics that quietly changed the expansion in a way our theories do not yet include. Nobody knows. The two numbers simply sit there, 73 and 67, patient and immovable, like two witnesses to the same event who cannot be persuaded to tell the same story, quietly insisting that there is something about our own expanding universe that we still do not understand. Now let us turn to a mystery that is, in a sense, the most personal of them all, because it is the reason you exist at all. It is the puzzle of why there is anything here to be made of, why there is matter in the universe. And to feel the strangeness of that question, we have to talk gently about matter's mirror twin, a shadowy counterpart called antimatter. The story begins with a piece of pure mathematics. In 1928, a famously quiet English physicist named Paul Dirac, born in 1902, was working out an equation to describe the electron, that tiny particle of negative charge that swirls around every atom. His equation was beautiful and it worked, but it had a peculiar feature. It seemed to insist that for the ordinary electron there must also exist a kind of mirror image partner, a particle with the same mass, but the opposite charge. At the time this sounded almost absurd, a mathematical ghost with no home in the real world. But Dirac trusted his equation, and just 4 years later, in 1932, an American physicist named Carl Anderson, studying the particles that rain down on us from space, found it. A particle exactly like an electron, but positively charged. He called it the positron, and it was the first piece of antimatter ever discovered. Dirac's mathematical ghost was real. We now know that antimatter is a genuine and general feature of nature. Nearly every kind of particle has an antiparticle, a twin identical in mass, but opposite in certain properties, like electric charge. And here's the crucial, dramatic thing about matter and antimatter. When a particle meets its antiparticle, they annihilate. They do not simply collide or bounce. They vanish. Both of them, their entire mass, converted in an instant into a flash of pure energy. A burst of light. Matter and antimatter cannot coexist. To bring them together is to erase them both in a silent, brilliant flash. Now hold that fact in your mind and turn it toward the birth of the universe. In the tremendous heat and energy of the earliest moments after the Big Bang, particles were being created in vast numbers out of raw energy. But here is the thing that our best physics insists upon. When you make particles out of pure energy, you make them in perfectly matched pairs, one particle and one antiparticle every single time. Energy turning into matter should always produce exactly equal amounts of matter and antimatter, and so the early universe should have been born with precisely as much antimatter as matter, equal partners in perfect balance. But if that were truly so, you would not be here to hear this, because as the young universe expanded and cooled, all that matter and antimatter created in equal amounts should have found each other and annihilated, every particle meeting its twin, every pair vanishing into light. The universe should have ended up as nothing but a fading sea of radiation, a vast bath of light with no matter left at all, no galaxies, no stars, no planets, no people, just light, spreading out and dimming forever in an empty cosmos. By the simplest reading of the laws we know, the universe should be empty. And yet look around. Here is a world of solid matter. Here are stars and oceans and hands and eyes. Matter clearly won. Somehow in the great annihilation of the early universe, a tiny sliver of matter survived, and everything you have ever seen or touched is built from that sliver. The question, the deep and beautiful question, is how? How did matter come to outnumber antimatter when the two were supposed to be born in perfect balance? The answer, as far as we can tell, is that the balance was not quite perfect. There was, it seems, a very slight favoring of matter over antimatter, an almost imperceptible imbalance woven into the physics of the early universe. The numbers involved are staggering in their delicacy. It appears that for every billion particles of antimatter, there were about 1,000,000,001 particles of matter. So when the great annihilation came, and the billions of pairs destroyed each other in light, that one extra particle of matter in every billion was left standing, with no antimatter partner to cancel it out. And that faint residue, that one part in 1,000,000,000 that survived, became everything. Every galaxy, every star, every atom in your body is made from the tiny surplus that was left over after the great mutual erasure. You are quite literally the rounding error of the early universe. The little bit that did not cancel. The mystery is why that imbalance existed at all. What tipped the scales ever so slightly toward matter? In 1967, a brilliant Soviet physicist named Andrei Sakharov, born in 1921, a man who would later become as famous for his conscience and his campaigns for peace as for his physics, laid out the conditions that would have to be met for such an imbalance to arise from a balanced beginning. His work showed that the laws of nature must contain a subtle, built-in preference, a slight asymmetry between matter and antimatter, a way in which the two twins are not perfectly identical after all. And astonishingly, physicists have found exactly such an asymmetry in delicate experiments with certain unstable particles. As early as 1964, two American physicists, James Cronin and Val Fitch, discovered that certain particles decay in a way that very slightly violates the perfect symmetry between matter and antimatter, a phenomenon known as charge parity violation. It was a real crack in the mirror, a genuine sign that nature does, very faintly, treat matter and antimatter differently. And yet, here is the frustration that keeps this mystery alive. The small asymmetry we have found in our experiments, that faint crack in the mirror, is nowhere near large enough to explain the imbalance we see in the universe. It can account for only a tiny fraction of the matter that survived. Something more must have been at work in the early cosmos, some deeper source of asymmetry that we have not yet discovered, some further way in which matter and antimatter part company. We know the imbalance happened because we are here. We have even found hints of how it might work, but the full explanation, the complete reason why the universe is made of something rather than nothing, why matter won its silent war against its own reflection, remains one of the great unsolved questions of physics. Every atom in you is a survivor of that ancient one-sided battle, and we still do not fully know why you were spared. Let us move now from the deep past to something that is happening right now, tonight, all across the sky, and that we have only very recently learned to notice at all. It is a mystery made of sound in a way, though not sound you could ever hear. It is made of radio waves, and it arrives in sudden, brilliant, fleeting flashes from the far reaches of the universe. Astronomers call them fast radio bursts, and they are among the newest and most tantalizing puzzles in all of science. To understand them, set aside visible light for a moment and think about radio waves, which are simply another kind of light, a form our eyes cannot see but our instruments can. Great radio telescopes, huge dishes pointed at the heavens. Listen to the sky in these longer wavelengths, picking up the faint radio hum of distant galaxies, spinning stars and clouds of gas. It is usually a slow and steady kind of listening, a patient gathering of faint signals over long stretches of time. And then, in 2007, an astronomer named Duncan Lorimer, examining old recordings from a great radio telescope in Australia called Parkes, found something that did not belong. It was a burst, a single enormous spike of radio energy that had lasted just a few thousandths of a second and then vanished. In that tiny flicker of time, this burst had released a staggering amount of energy, as much as our sun pours out over many days or even years, all packed into a flash shorter than a blink. And it had come, judging by its characteristics, from far outside our galaxy, from somewhere deep in the distant universe. It was so brief, so bright, and so strange that at first many astronomers wondered whether it was real at all or some glitch in the instruments, some local interference dressed up as a cosmic event. For a while these signals were treated with deep suspicion, but then more of them turned up in data from telescopes around the world, and it became undeniable. These fast radio bursts were real, and they were coming from the cosmos. And as astronomers built new instruments designed specifically to catch them, they discovered something remarkable about how common they are. It is now believed that these bursts are going off across the sky constantly, perhaps hundreds or even thousands of times every single day, in every direction. Brief flares of radio light from the depths of the universe that we had simply never known to look for. The sky, it turns out, has been quietly crackling with them the whole time. There is a beautiful detail in how these bursts reveal their distance, and it is worth savoring slowly. As a burst of radio waves travels across the vast reaches of space, it passes through the thin scattering of particles that drifts between the galaxies. And this thin cosmic haze affects the different frequencies of the radio wave by slightly different amounts, so that the higher notes of the burst, so to speak, arrive a fraction of a moment before the lower notes. The burst gets smeared out in a very particular way, like a chord played on a piano, where the high keys reach you just before the low ones. By measuring exactly how smeared the burst is, astronomers can estimate how much space it has crossed, and therefore how far it has come. And the answer, again and again, is that these bursts have traveled from enormously far away, across billions of light years, from galaxies scattered throughout the distant universe. So what could possibly produce such a thing? What could release the energy of years of sunshine in a flash lasting 1,000th of a second from across the cosmos? For years, this was wide open, and the proposed explanations ranged from the plausible to the wild. Some astronomers thought of catastrophic events, the collapse or collision of extraordinarily dense stellar corpses. Others, only half in jest, wondered aloud whether some of them could be signals from distant civilizations, though there has never been evidence for such a thing. The mystery deepened further when astronomers discovered that while many bursts flash only once, never to be seen again, a few of them repeat, flaring up over and over from the same spot in the sky, which ruled out any explanation based purely on a one-time cosmic catastrophe, at least for those repeating sources. Then in 2020 came the strongest clue yet, and it arrived, thrillingly, from within our own galaxy. A burst went off much closer to home, and astronomers were able to trace it to a particular kind of object, a magnetar. A magnetar is the collapsed city-sized core left behind when a massive star dies, spinning fast and wrapped in a magnetic field of almost unimaginable strength, trillions of times stronger than the Earth, so powerful it strains the imagination. When this nearby magnetar released a burst of radio waves, it looked very much like a smaller cousin of the great fast radio bursts from distant galaxies. It was a genuine breakthrough, the first solid link between these mysterious flashes and a real, known kind of object. And yet, even with that clue in hand, the full mystery is far from solved. It is not at all clear that every fast radio burst comes from a magnetar. Even for those that do, no one fully understands exactly how a magnetar produces such a brilliant, precise flash of radio light. The repeating bursts and the one-time bursts may come from entirely different kinds of sources. So the picture remains gloriously incomplete right now as you lie here drifting towards sleep. Brief flashes of radio light are almost certainly washing over the Earth from the far corners of the universe, each one a tiny message from some violent, distant event we do not fully understand, arriving after a journey of billions of years, flickering through our instruments for 1,000th of a second and then gone. Our next mystery is written across the entire sky, on the oldest surface we can ever see, and to reach it we have to travel back to the earliest light in all of creation. So let us slow down and build this one gently, because the setting is one of the most beautiful ideas in science. Earlier tonight, when we spoke of the Hubble tension, I mentioned an ancient light left over from the Big Bang. Now we're going to sit with that light directly, because hidden within it is a cold, quiet puzzle that no one can quite explain. When the universe was very young, it was not the vast, dark, transparent space we see today. It was hot and dense and glowing, filled everywhere with a thick fog of particles and radiation, so crowded that light could not travel freely. A ray of light in that early universe would move only a tiny distance before being scattered, bouncing endlessly like a person trying to walk across a room packed shoulder to shoulder with people. The whole cosmos was an opaque, glowing mist, and then about 380,000 years after the beginning, as the universe expanded and cooled, something quietly momentous happened. It became cool enough for the particles to settle into stable atoms, and all at once the fog cleared. The crowd, so to speak, parted, and light could suddenly travel freely across space for the first time. That light, released at the moment the universe became transparent, is still traveling today. It has been crossing space for over 13 billion years, stretched out by the expansion of the universe into a faint glow of microwaves that now fills the entire sky in every direction. We call it the cosmic microwave background, and it is, quite literally, the afterglow of creation, the oldest light there is, a photograph of the universe as it was when it was only a few 100,000 years old. It surrounds us completely, coming from every part of the sky at once, a faint, cold whisper of radiation left over from the dawn of everything. It is astonishingly uniform, almost exactly the same temperature in every direction. A gentle, even hum of ancient light, sitting at a chilly 2 and a bit degrees above the coldest possible temperature. But not perfectly even, and this is where it becomes interesting. When astronomers built spacecraft sensitive enough to map this ancient light in fine detail, first a satellite called WMAP in the early 2000s, and later the even sharper European Planck satellite, they found that the temperature of this afterglow varies ever so slightly from place to place across the sky by tiny fractions of a degree. These faint ripples are precious beyond words. They are the seeds of everything, the slightly denser and slightly thinner patches in the infant universe that would, over billions of years, grow into all the galaxies and great cosmic structures we see today. Reading those ripples is like reading the blueprint of the cosmos. And for the most part, they look exactly as our theories predict. A random, gentle speckling of warmer and cooler spots, statistically well behaved, beautifully in line with expectation. Except for one place. In the map of that ancient light, in a particular region of the southern sky, toward the constellation of Eridanus, there is a spot that is larger and colder than it has any right to be. Astronomers call it simply the cold spot. It is a broad patch of the ancient sky where the afterglow dips cooler than the average over a region far bigger than the ordinary ripples, a cold blotch on the face of the infant universe that our standard picture struggles to account for. It was first noticed in the WMAP data around 2004, and when the sharper Planck satellite later mapped the same sky, the cold spot was still there, stubborn and real, not an error of the first instrument, but a genuine feature of the oldest light. Now, how unusual is it, really? This is where astronomers become careful, and where the mystery becomes subtle rather than sensational. The universe is enormous, and the sky is large, and in any random speckled pattern, you will occasionally find a spot that looks surprising just by chance. If you scatter enough grains of sand, you will now and then find a little cluster that seems too dense to be accidental, even though it is. So one entirely reasonable possibility is that the cold spot is simply a rare but natural fluctuation, an unlucky roll of the cosmic dice, a patch that looks strange but means nothing deeper. Many astronomers lean toward exactly this explanation, and it may well be the right one. But others are not so sure, because the cold spot seems a little too cold and a little too large to sit comfortably as mere chance, and so people have searched for a physical cause. One leading idea is that between us and that patch of ancient light, there lies an enormous, unusually empty region of space, a great cosmic void with far fewer galaxies than normal, sometimes called a supervoid. When the ancient light passes through such a vast emptiness on its long journey to us, the expansion of the universe can subtly drain a little energy from it, cooling it slightly and casting a kind of cold shadow on that part of the sky. Astronomers have indeed found signs of a large, underdense region in roughly the right direction. But whether it is empty enough and large enough to fully explain the cold spot remains genuinely disputed, and the numbers do not quite seem to add up. And then there are the wilder ideas, the ones spoken of more cautiously in the quieter corners of cosmology. A few physicists have wondered whether the cold spot could be something far stranger, a faint bruise left on our universe by a collision with another universe entirely. In theories where our cosmos is only one bubble among many, there is no good evidence for such a thing, and most scientists regard it as the most speculative of long shots. But the very fact that serious people have raised it tells you something about how genuinely puzzling that cold patch is. A statistical fluke, a shadow cast by a great emptiness, or a bruise from another universe. Somewhere on the oldest light in existence, there is a cold, quiet spot, and we still cannot say for certain why it is there. Our next mystery is perhaps the most disputed of all, a claim so strange that many astronomers doubt it is real at all, and yet so intriguing that it refuses to fully go away. It has a wonderfully evocative name. It is called dark flow. And to feel what it proposes, we need to think about the different ways things can move in the universe. We have already talked about the great expansion, the way space itself is swelling and carrying the galaxies apart. That is one kind of motion, the general drifting apart of everything as the cosmos grows. But galaxies also move in a second way, a more local way, drawn this way and that by the gravity of their neighbors, tugged toward great concentrations of mass, pulled into slow cosmic currents by the uneven distribution of matter around them. Our own galaxy, for instance, is being pulled through space toward a distant, dense concentration of galaxies, a great gravitational draw in one particular direction. These local motions laid over the top of the general expansion are perfectly expected. Gravity pulls, and things drift toward mass. There is nothing mysterious in that. What would be mysterious, deeply mysterious, is if a vast collection of galaxy clusters spread across an enormous swath of the universe were all found to be drifting together in the same direction, toward the same distant patch of sky at the same steady speed, as though something were pulling on all of them at once from far beyond the edge of everything we can see. Not each cluster tugged by its own local neighbors, but all of them over a huge region, streaming in unison toward a single point on the horizon of the observable universe. That is precisely what an astronomer named Alexander Kashlinsky and his colleagues claimed around 2008 to have detected. Their method was ingenious and delicate. They looked at how the ancient afterglow of the Big Bang, that same cosmic microwave background we just visited, is very slightly shifted when it passes through the hot gas inside great clusters of galaxies. By carefully studying that faint shift for many hundreds of clusters spread across the sky, they believed they could detect the collective motion of all those clusters through space. And what they reported was startling. The clusters, they claimed, were not moving randomly, nor merely being carried apart by expansion. They seemed to be flowing together coherently toward a particular region of the sky at a speed that the ordinary gravity of the visible universe could not explain. A great, silent migration of galaxy clusters, all drifting the same way, for no reason our maps of the cosmos could account for. Why would that be so shocking? Because within our observable universe there does not appear to be enough unevenness in the distribution of matter to pull so many clusters across such a vast region in the same direction at once. If the dark flow were real, the pull would seem to be coming from somewhere else, from beyond the edge, from outside the part of the universe we can ever see. And this is where the idea becomes almost dizzying. Because of the finite speed of light and the finite age of the universe, there is a limit to how far we can see in any direction, a horizon beyond which the light has simply not had time to reach us. The dark flow, if it were real, might be a sign that something enormous lies beyond that horizon, some vast concentration of matter, or some feature left over from before the universe as we know it began, tugging on our region of the cosmos from a place we can never directly observe. It would be a rumor reaching us through the motion of galaxies, of a universe far larger and stranger than the part we can see. You can perhaps feel why this claim electrified some people and deeply troubled others. It is a beautiful and unsettling idea, a whisper of the beyond. But extraordinary claims demand extraordinary evidence, and the dark flow has not, so far, provided it. The measurement is fiendishly difficult, right at the ragged edge of what our instruments can detect, and the faint signal Kashlinski's team reported is very hard to separate cleanly from noise and from other effects. When the team behind the Sharper Planck satellite later examined the question with their own superb data, they reported that they saw no convincing evidence for such a flow and concluded that the earlier signal might not be real at all. Others have continued to argue that some trace of it remains. And so the dark flow sits in a strange limbo, neither confirmed nor entirely dismissed, a claimed cosmic current that may be one of the most profound discoveries in the history of astronomy, or may simply be a mirage born of the extraordinary difficulty of the measurement. That uncertainty is itself worth sitting with, softly as you rest. Not every mystery in science is a clean, confirmed fact waiting to be explained. Some are like this one, a possible signal, glimpsed at the very limit of what we can measure, hovering between discovery and illusion, requiring years of patient work simply to decide whether there is anything there at all. The dark flow may be nothing, or it may be a faint tug from beyond the edge of the visible world, the gentlest possible hint that the universe does not end where our sight ends, that there is more out there pulling quietly on everything forever beyond our reach. We do not yet know. And there is a kind of peace in being allowed tonight to simply not know. Now we come to what may be the largest and most confounding mystery of them all, larger even than the dark matter we began with, because it makes up more of the universe than anything else, and we understand at least. It hides inside that same expansion of the cosmos we have been circling all night, and its discovery upended what everyone thought they knew about the fate of everything. For most of the 20th century, astronomers assumed the expansion of the universe must be gradually slowing down. It seemed obvious. All the matter in the cosmos, all the galaxies, pull on one another with gravity, and gravity is always attractive, always pulling things together. So the expansion set off by the Big Bang should, like a ball thrown into the air, be steadily decelerating as gravity tugged everything back. The only real question, people thought, was whether gravity would one day win and pull everything back together, or whether the universe would keep coasting outward forever, ever more slowly. To settle that question, two rival teams of astronomers in the 1990s set out to measure precisely how much the expansion was slowing down. They used those reliable exploding stars, the type Ia supernovae, as beacons to measure the expansion at great distances, and therefore far back in time. One team was led by Saul Perlmutter, born in 1959, and the other by Brian Schmidt, born in 1967, working alongside the same Adam Rees we met during the Hubble tension. Both teams were hunting for the same thing, the gentle slowing of the cosmos. And in 1998, both teams found the same astonishing result, a result so contrary to expectation that they each spent months anxiously checking for errors before they dared to believe it. The distant supernovae were fainter than they should have been. They were farther away than a steadily slowing universe could explain. The expansion of the universe was not slowing down at all. It was speeding up. Something was pushing the cosmos apart faster and faster, overwhelming the inward pull of all the matter's gravity, accelerating the growth of space itself. Let that sink in slowly, because it is genuinely one of the most unexpected discoveries in the history of science. Every galaxy is not merely drifting apart. It is drifting apart at an ever-increasing pace, as though some invisible pressure fills all of empty space, pushing outward, gently but relentlessly, on the entire universe at once. The astronomers who made this discovery, Perlmutter, Schmidt, and Rees, were awarded the Nobel Prize in Physics in 2011 for it, and the mysterious something doing the pushing was given a name that, like dark matter, is really just a placeholder for our ignorance, and they called it dark energy. Here's how strange the accounting has become. When cosmologists add everything up, all the ordinary matter of stars and planets and gas and people comes to only about 5% of the universe. The invisible dark matter we spoke of earlier comes to about 27%. And all the rest, the remaining 68% or so of everything that exists, is this dark energy, this pressure in the vacuum driving the acceleration. So the universe is dominated overwhelmingly by two things we cannot see and do not understand. Ordinary matter, the entire visible cosmos of glowing stars and galaxies. Everything we have ever photographed or touched is a faint 5% skin on a cosmos made almost entirely of darkness in two unknown forms. We are latecomers to a universe whose main business is being conducted by things we have no name for, beyond the word dark. So what is dark energy? The simplest idea is also one of the oldest, and it traces back to Albert Einstein. When Einstein first wrote down his equations describing gravity in the universe, back in 1917, he added a small term, a kind of constant background pressure built into space itself, which he called the cosmological constant. He introduced it for reasons that later seemed mistaken, and for decades, it was regarded as an embarrassing wrinkle, a fudge factor to be set to zero and forgotten. But the discovery of the accelerating universe brought it roaring back to life, because a constant energy woven into the fabric of empty space, pushing gently outward everywhere, is exactly what you would need to drive the acceleration. Empty space, in this picture, is not truly empty. Even a perfect vacuum, with every particle removed, might still contain a faint, irreducible energy of its own, a pressure inherent in nothingness. And it is that energy of empty space, multiplied across the unimaginable volume of the cosmos, that is pushing the galaxies apart. It is a lovely idea, but it leads directly into what many physicists consider the single most embarrassing failure in all of science. When they try to calculate from the known laws of quantum physics how much energy empty space ought to contain, they get an answer. And that answer is wrong, not a little wrong. It is wrong by a factor so enormous that it defies comprehension. A number followed by something like 120 zeros too large. The theoretical prediction for the energy of empty space and the actual measured value of dark energy disagree by more orders of magnitude than there are atoms in and a great many galaxies. It has been called, only half in jest, the worst prediction in the history of physics. Somehow, the vast energy that quantum theory says should fill every scrap of empty space is almost, but not quite, perfectly canceled out, leaving behind just the tiny, gentle whisper of pressure that is pushing our universe apart. Why it is canceled so precisely, and why not completely, nobody knows. And the mystery has teeth that reach into the far future, because the fate of the entire universe depends on the nature of this thing we cannot explain. If dark energy stays constant, the acceleration will continue, and over unimaginable stretches of time, the galaxies will be carried so far apart that the sky will slowly empty out, each galaxy eventually alone in an ever-darkening void. If dark energy grows stronger over time, some have imagined an even more dramatic end, in which the acceleration eventually becomes so fierce that it tears apart galaxies, then stars, then atoms themselves. And if it were somehow to weaken or reverse, the whole expansion could one day turn around. Which of these will happen depends entirely on what dark energy truly is, and that is a question we cannot yet answer. The largest ingredient of the universe, the thing that will decide how all of this ends, is a mystery we have barely begun to understand, hiding in the empty space between the words you are hearing, pushing ever so gently on everything there is. Let us turn now to a smaller mystery, quieter and more technical than the great darknesses, but beloved by cosmologists precisely because it is so sharp and so stubborn. It lives in the first few minutes of the universe, and it concerns a simple question of counting. How much of each kind of atom did the Big Bang actually make? And the puzzle is that for almost everything, our answer is triumphantly right, and for one small thing, it is stubbornly, mysteriously wrong. Go back to the very early universe, just the first few minutes after the beginning, when everything was still ferociously hot and dense. In those first minutes, before any star had formed, the whole cosmos behaved like a single vast furnace, hot enough for the simplest nuclear reactions to take place everywhere at once. Protons and neutrons, the building blocks of atomic nuclei, were colliding and sticking together, forging the very first atomic nuclei out of the raw particles of creation. This process, in those opening minutes, is called Big Bang nucleosynthesis, and it is one of the great triumphs of cosmology, first worked out and outlined by physicists, including George Gamow and his student Ralph Alpher in the late 1940s. Within just a few minutes, before the universe expanded and cooled too much for the furnace to keep burning, it had produced a specific mix of the lightest elements, mostly hydrogen, a good deal of helium, and faint traces of a few others. And here's the beautiful part. Our theory of those first few minutes makes very precise predictions about exactly how much of each light element should have been produced. It predicts that about 3/4 of the ordinary matter should be hydrogen, and about 1/4 should be helium, with only the tiniest sprinkling of anything heavier. And when astronomers go out and measure the actual amounts of hydrogen and helium in the most ancient, pristine gas they can find, gas that has barely been touched since the beginning, the numbers match the predictions superbly. It is one of the strongest pieces of evidence we have that the Big Bang really happened. This stunning agreement between a theory of the first 3 minutes and the composition of the oldest matter in the cosmos, by any measure, it is a resounding success, except for lithium. Among the trace elements the Big Bang should have forged is a small amount of a light metal called lithium, specifically a form of it called lithium 7. Our theory predicts quite precisely how much of it those first minutes should have made. And when astronomers go looking for that primordial lithium in the atmospheres of the oldest, most pristine stars they can find, ancient stars that formed from nearly untouched early material, they find only about a third as much as the theory says there should be. Not a little less. Roughly 3 times less. The hydrogen matches. The helium matches beautifully. But the lithium is off by a factor that simply will not go away, no matter how carefully the measurements and the calculations are checked. Cosmologists call it plainly the lithium problem. It is a strange and specific little wound in an otherwise triumphant theory. Everything about our picture of the first 3 minutes works, except for this one element present in the wrong amount by a factor of 3, and the explanations proposed span the full range of possibility. Perhaps we are misreading the lithium in those ancient stars, and some process inside the stars themselves has quietly destroyed or hidden a portion of their original lithium over the billions of years, so that what we measure today is not the true primordial amount. Perhaps there is some subtlety in the nuclear reactions of the early universe that we have not quite got right. Or perhaps, and this is the tantalizing possibility, the discrepancy is a genuine crack, a hint that something unknown, some new particle or new physics, was at work in those first minutes, subtly altering the recipe. The lithium problem is small, but it is precise, and precise problems are the ones that sometimes crack open into something large. For now it simply sits there, a single element counted 3 times too few, quietly refusing to fit. While we are near the ancient afterglow of the Big Bang, there is one more puzzle written on that oldest light, a cousin of the cold spot, and in its own way even more unsettling to cosmologists. It has to do not with a single strange patch, but with a strange sense of direction in the universe as a whole. To feel why it matters, we have to start from a principle so basic that it underlies nearly all of modern cosmology. That principle is simply this: the universe should have no preferred direction. On the largest scales, it should look essentially the same whichever way you turn, with no special axis, no up or down, no favored orientation woven into the fabric of space. This idea that the cosmos is the same in all directions is one of the deep assumptions on which our whole understanding rests, and for the most part the evidence supports it beautifully. The galaxies are scattered evenly across the sky. The ancient afterglow glows at nearly the same temperature in every direction. There is no cosmic north, no grand arrow pointing the way. The universe appears magnificently indifferent to direction. And yet when cosmologists looked very carefully at the largest scale patterns in that ancient light, the broadest ripples spread across the whole sky, they found something they did not expect. Some of those largest patterns seemed to line up with one another, to share a common orientation, pointing along a particular axis in space, as though the infant universe had a faint preferred direction after all. The alignment was strange enough and troubling enough to our assumption of a directionless cosmos that a pair of physicists gave it a deliberately provocative name in 2005. They called it the Axis of Evil, a half-joking title for a genuinely serious puzzle. There were other oddities too, hints that one half of the sky carried slightly more of these ancient ripples than the other, a faint lopsidedness in a universe that was supposed to be perfectly even-handed. Now, as with the cold spot, the great question is whether any of this means anything. The most sober explanation is once again the roll of the dice. When you look at the very largest patterns in the sky, there are only a handful of them to examine, and with so few to work with, apparent coincidences and alignments can crop up purely by chance, the way a small handful of coin flips can easily come up, mostly heads without anything being wrong with the coin. Many cosmologists suspect that these alignments are exactly this kind of statistical accident, a trick of having only one sky to look at. Others worry that some of the effect might come from imperfectly removed contamination, faint foreground, glows from our own galaxy or solar system bleeding into the ancient map. But here is what keeps the puzzle alive. When the superbly precise Planck satellite remeasured the whole sky, expected by many to wash these anomalies away as artifacts of the earlier, cruder maps, the strange alignments and the lopsidedness did not vanish. They remained stubbornly in the sharper data. That does not prove they are meaningful. A rare fluke will persist, no matter how well you measure it. But it does mean they cannot be dismissed as mere instrumental error. And so there lingers a quiet, uncomfortable possibility that the largest scale structure of the cosmos carries a faint imprint of direction that our theories say should not be there, a subtle signature we cannot yet explain, written into the oldest light in the universe. A cosmos that is supposed to have no preferred direction seems, just possibly, to be whispering one, and we do not know why. Let us pause here for a slow moment and notice something about the mysteries we have gathered so far, because a quiet pattern runs through many of them. Again and again tonight we have found that the universe we can see, the bright and touchable universe of stars and atoms and light, is only a thin surface over something vast and hidden. Dark matter holds the galaxies together, unseen. Dark energy pushes the whole cosmos apart, unseen. Together, those two darknesses make up about 95% of everything there is, and we cannot say what either of them truly is. We have spent all of human history studying the remaining 5%, the little glowing rim of the possible, and mistaking it for the whole. It is a humbling thing to sit with. Nearly everything is made of something we have not yet learned to name, and there is a strange comfort in that humility, if you let there be. We tend to imagine that science is mostly a story of answers, of mysteries conquered and closed. But the deeper truth, the one the working astronomers live inside every day, is that the questions keep getting larger, not smaller, the more we learn. Every answer opens a wider door. Understanding that the galaxies spin too fast led us to dark matter, and dark matter led us to realize we do not know what most of matter is. Measuring the expansion led us to dark energy, and dark energy led us to the worst prediction in physics. The universe rewards our curiosity not with tidy conclusions, but with grander mysteries, and there is something almost generous in that. As though the cosmos will never run out of things to wonder about, no matter how long we look. Which brings us, naturally, to the oldest and largest question of all, the one that sits underneath every other mystery of the night. Where did all of this come from? What happened at the very beginning? And if you dare to ask it, what came before? We can trace the story back a very long way. By measuring the expansion and the ancient afterglow and the amounts of the light elements, cosmologists have pieced together a remarkably detailed history of the universe stretching back some 13.8 billion years to a time when everything was compressed into an unimaginably hot, dense state, and then began to expand and cool into the cosmos we know. That expansion from a hot, dense beginning is what we call the Big Bang, and the evidence for it is overwhelming. But when we try to run the story all the way back to the very first instant, to the beginning of the beginning, our finest theories stop working. The mathematics that describes gravity and space and time, the equations that serve us so beautifully everywhere else, break down completely at that first moment, giving nonsensical, infinite answers. We reach a wall beyond which our physics simply cannot see. To describe what happened at that very first instant, we would need a theory that unites the physics of the very large, gravity and space and time, with the physics of the very small, the quantum world of particles. And despite a century of effort by the most brilliant minds alive, we do not yet have such a theory. So the truthful answer to the question of what happened at the very first moment of the universe is that we do not know. We can describe the universe from a tiny fraction of a second onward with astonishing confidence. But that first fraction of a second, the doorway through which everything came, remains hidden behind a wall our current understanding cannot cross. And the question of what came before is stranger still, so strange that it may not even be a proper question. Because according to our best understanding, time itself may have begun with the universe. In that view, asking what came before the Big Bang is a little like standing at the North Pole and asking which way is further north. There is no further north. The question dissolves. There may simply be no before, no earlier moment in which anything could have happened, because moments themselves only began when the universe did. Other physicists suspect the opposite, that our Big Bang was not the absolute beginning, but one event in a much longer story, perhaps a bounce from an earlier contracting universe, or one bubble among countless others in a vast and eternal cosmos, endlessly giving birth to new universes. There are beautiful, careful, competing ideas, and at present no way to choose between them. The single most fundamental question we can ask, why there is a universe at all and how it began, sits tonight exactly where it has always sat, just beyond the reach of everything we know. There is another place in the universe where our physics breaks down completely, and unlike the beginning of time, these places are scattered all through the cosmos right now, waiting. They are black holes, and they hold a mystery so sharp that it has divided the greatest physicists of our age for half a century. You likely know the basic picture. A black hole is a region where matter has collapsed so completely and gravity has become so overwhelmingly strong that nothing can escape it, not even light. It is bounded by a kind of one-way surface called the event horizon, a point of no return. Cross it, and there is no coming back, no signal you could send, no light you could shine that would ever climb back out. For a long time, these were purely theoretical, but we now know beyond doubt that they are real. They sit at the centers of galaxies, including our own, where a black hole, millions of times the mass of the sun, holds sway. And in 2019, a globe-spanning network of telescopes working together produced the first actual image of one, a dark circle ringed by glowing gas in a distant galaxy. The reality of black holes is no longer in question. What happens inside them and what they mean for the laws of physics very much is. The first mystery is simply what lies at the center. According to our theory of gravity, when matter collapses into a black hole, it keeps collapsing, all the way down, until it is crushed into a point of infinite density, a place where space and time curve infinitely, and the equations once again give nonsensical, infinite answers. This point is called a singularity, and its appearance is really a confession that our theory has broken. No one believes matter truly becomes infinitely dense. It is far more likely that something else happens down there, something governed by that missing theory of quantum gravity we do not yet possess. So at the heart of every black hole, hidden forever behind the event horizon, there is a place where the known laws of physics simply stop, and we have no way to see in and find out what replaces them. But the deepest black hole mystery is subtler, and it grew from a startling discovery by the physicist Stephen Hawking, born in 1942. For a long time, black holes were thought to be perfectly, permanently black, swallowing everything and giving nothing back. But in 1974, Hawking showed, by combining the physics of gravity with the physics of the quantum world, that black holes are not entirely black after all. Because of subtle quantum effects right at the event horizon, a black hole should very slowly leak a faint trickle of radiation, glowing almost imperceptibly, losing a tiny bit of energy and therefore a tiny bit of mass over time. Over unimaginably long stretches of time, far longer than the current age of the universe, this means a black hole will slowly evaporate, shrinking bit by bit until at last it disappears entirely. Black holes, it turns out, are not eternal. They fade. And that is where the paradox strikes, one of the sharpest in all of physics. One of the deepest principles in the quantum world is that information is never truly destroyed. The precise details of whatever falls into any physical process are, in principle, always preserved, scrambled perhaps beyond recognition, but never erased. Now think about what happens with an evaporating black hole. All sorts of things fall in: stars, gas, whole libraries of intricate detail, all the information of everything that ever crossed the horizon. And then the black hole slowly evaporates away into that faint Hawking radiation, which appears to carry no memory of what fell in. And finally it vanishes altogether. So where did all the information go? If it was truly inside the black hole, and the black hole is now gone, then the information seems to have been destroyed, which quantum physics says is impossible. But if the information somehow escaped, we cannot see how it climbed back out from behind a horizon that lets nothing escape. This is the black hole information paradox, and it pits two of our most trusted pillars of physics directly against each other. It is not a small technical quibble. It cuts to the heart of whether our two greatest theories, quantum physics and Einstein's gravity, can truly be reconciled, and physicists have wrestled with it for 50 years without full resolution. Some now believe the information does escape, subtly encoded in the radiation in ways we are only beginning to understand. And recent years have brought tantalizing progress in that direction, but there is still no complete, agreed-upon answer. Every black hole in the sky, and there are many, is a place where our deepest laws come into open conflict, a dark sphere holding a contradiction we have not yet learned to resolve. They are, in a sense, the universe's way of telling us that our understanding, for all its power, is still incomplete. Here is a mystery of a very different flavor, one that is less about equations and more about a strange ringing silence. It is perhaps the most human of all the cosmic questions because it asks whether we are alone. And its puzzle is not that we have found nothing, but that finding nothing is itself deeply surprising. Consider the sheer scale of things. Our galaxy, the Milky Way, contains something like a few 100 billion stars, and we now know that planets are common. that most of those stars have worlds of their own, and that a good many of those worlds are, in size and warmth, not so unlike the Earth. The galaxy is also very old, far older than our Sun, so that countless of those worlds have had billions of years more time than we've had to develop life, and perhaps intelligence, and perhaps the ability to build ships or send signals across the stars, and even a civilization spreading slowly, patiently, from star to star over the ages would need only a few million years, a mere eye blink compared to the age of the galaxy, to cross the entire Milky Way from end to end. By that reasoning, the galaxy should be teeming, should have been visited or settled, or at least heard from many times over. The physicist Enrico Fermi, born in 1901, is said to have summed up the whole puzzle over lunch one day, in 1950, with a single, simple, devastating question. Where is everybody? Because the sky so far is silent. For decades now, astronomers have listened patiently with radio telescopes for any deliberate signal, any greeting or beacon or stray broadcast from another civilization, and they have heard nothing that stands up as a message. We have found no clear sign of any technological civilization anywhere. Not a whisper, not a probe, not a structure. The universe, as far as our instruments can tell, appears to be quiet. This gap between the expectation of abundance and the reality of silence is what people call the Fermi paradox, and the emptiness where a chorus of voices might have been is sometimes called the Great Silence. And the possible explanations are, in their way, some of the most sobering and fascinating ideas anyone has ever entertained, because every one of them tells us something about our own place and fate. Perhaps life itself is far rarer than we imagine, and the chain of accidents that led from lifeless chemistry to a creature that can wonder about the stars is so improbable that it has happened only vanishingly seldom. Perhaps simple life is common, but the leap to complex, intelligent, technological life is the true rarity, a bottleneck almost never passed. Perhaps civilizations do arise, but tend to destroy themselves or fall silent, not long after they gain the power to be heard, so that the galaxy is dotted with the quiet ruins of the ones who came before. Or perhaps they are out there, and we simply do not yet know how to listen, or they have no wish to announce themselves to a young world like ours. Each of these answers carries a very different meaning for what lies ahead of us, whether we are precious and nearly alone, or merely early, or standing before a filter that few survive. We do not know which, if any, is true. It is entirely possible that somewhere out there, on some world circling a star you could see from your window, on a clear night, another creature is lying awake, wondering the very same thing about us, and that the distances and the timing have simply never allowed the two of us to meet. Or it may be that for reasons we do not yet grasp, the gift of looking up and wondering is far rarer and more fragile than it feels. Either way, it lends a certain tenderness to this quiet night. Whether the universe is crowded with hidden company or almost entirely still, the wondering itself, the very act of lying here and asking, is a rare and precious thing. And for tonight, it is enough simply to be one of the minds through which the cosmos gets to ask whether it is alone. We have wandered from the beginning of the universe to the silence between the stars. And now, as the night deepens, let us turn gently to the very end. Not the end of tonight, which will come softly and soon, but the end of everything, the ultimate fate of the cosmos, which is itself one of the great open questions, hanging on that mysterious dark energy we spoke of earlier. It sounds like it should be a heavy subject, but told slowly, from a great enough distance, it becomes strangely peaceful, the way even the largest things do when they are far enough away. As best we can tell, given a universe whose expansion is accelerating, the most likely future is a slow, quiet fading. Not a bang, but a long, gradual dimming. Over the coming billions of years, the accelerating expansion will carry the distant galaxies ever farther from one another, faster and faster, until eventually they are receding so quickly that their light can no longer reach across the widening gulfs between them. One by one, over immense stretches of time, the other galaxies will slip beyond the horizon of what can be seen, until a future astronomer in some far distant age would look out and find the sky beyond their own galaxy simply empty, the rest of the universe having quietly withdrawn beyond all possible sight. And within the galaxies that remain, the lights will slowly go out. Stars are born from clouds of gas, and that gas is finite. Over trillions of years, far longer than the mere 13 billion years the universe has so far lived, the gas will be used up. The last new stars will form and then age, and one by one the existing stars will exhaust their fuel and fade. The brilliant, blazing era of starlight that we happen to live in and take for granted as simply what a universe looks like is actually a brief early chapter of flickering dawn. The universe will spend almost all of its future not as a place of shining stars, but as a vast, cooling darkness scattered with the dim embers of dead suns, slowly drifting and slowly cooling toward a deep and uniform cold. Physicists have a name for this long, quiet fading. They call it the heat death, or sometimes more gently, the big freeze. It is the state the universe drifts toward if the expansion simply continues. Everything spreading out and cooling down, all the concentrated energy of stars and structure gradually smoothing away into a thin, even, lukewarm nothing, until at last there are no differences left anywhere, no hot and cold, no motion, no change, just a cold and perfect stillness, stretching on forever. Even the black holes, those most durable of all objects, will eventually evaporate away by that faint Hawking glow, over spans of time so long they make the current age of the universe seem like a single heartbeat. In the deepest future, there may be nothing left at all but a thin, cold whisper of light spread evenly through an endless dark. But even this is not certain because it depends entirely on the nature of dark energy, which we admitted we do not understand. If dark energy holds steady, the long, slow freeze is the likely end. If dark energy grows stronger with time, some have imagined a more violent finale in which the acceleration eventually becomes so overpowering that it tears apart first the galaxies, then the stars, then the planets, and finally atoms themselves, an ending sometimes called the Big Rip. And if dark energy were somehow to fade or reverse, the expansion could one day halt and turn back, drawing everything together again into a final hot collapse, a mirror of the Big Bang called the Big Crunch. Which of these endings awaits, if any, is written in the true nature of that mysterious dark energy. And so the fate of literally everything rests on a question we cannot yet answer. There is no need to feel the weight of any of this tonight. These are events unimaginably far off, separated from you by numbers of years so vast that they lose all meaning, and you will rest and wake and live your whole life, and so will every generation you can imagine, long, long before any of it comes to pass. If anything, there is a strange comfort in it. You happen to be alive in the bright morning of the cosmos, in the rare and fleeting age when the stars still shine, when there are still mysteries to look up at and wonder about. That is not a small thing. It is perhaps the most precious accident there is. Before we begin our long, slow descent into sleep, let me offer you one last mystery, and it may be the most intimate of all, because you are living inside it at this very moment. It is the mystery of why time flows the way it does, why there is a difference between the past and the future at all. Here's the strange thing that troubles physicists. Nearly all the fundamental laws of physics, the deep equations that govern particles and forces, work exactly the same whether you run time forward or backward. If you could film two atoms colliding and then play the film in reverse, nothing in the laws of physics would be violated. The reversed film would show a perfectly legal event. At the level of the smallest pieces, the universe does not seem to care which way time runs. The equations have no built-in arrow, no preferred direction, no sense of before and after. And yet your entire experience, every moment of your life is drenched in the difference between past and future. You remember yesterday, not tomorrow. A cup of hot tea cools to match the room and never spontaneously heats back up. A glass that falls and shatters never gathers itself back together and leaps into your hand. Eggs do not unscramble. We grow older, never younger. Time in lived experience has an unmistakable direction, a relentless one-way flow, even though the underlying laws do not. So where does that direction come from? The best answer we have points to a single deep idea, tied to that slow smoothing out we spoke of when we discussed the fate of the cosmos. It is called the increase of entropy, which is really just a precise way of talking about the tendency of things to move from order toward disorder, from concentrated to spread out, from arranged to jumbled. There are only a few ways for a stack of cards to be in perfect order, but countless ways for it to be shuffled, and so shuffling almost always leads toward the jumble simply because there is so much more jumble available. The one great physicist who first saw this clearly, the Austrian named Ludwig Boltzmann, born in 1844, showed that the forward direction of time is really the direction in which disorder increases, in which things spread out and even out and settle toward their most probable, most jumbled state. That is why the tea cools and the glass shatters, not because the laws demand it, but because disorder is overwhelmingly more likely than order, and so the world drifts, moment by moment, toward it. But this only pushes the mystery one step deeper, into a question that is genuinely unanswered. For disorder to be increasing now and to have been increasing all through the past, the universe must have begun in a state of extraordinarily low disorder, exquisitely ordered, almost impossibly special. The arrow of time we feel points away from that improbably neat beginning. And so the great unanswered question is why? Why did the universe begin in such a remarkably ordered, low disorder state in the first place? Why was the Big Bang so special? There is no accepted explanation. Our theories can tell us that disorder has increased ever since the beginning, and that this increase is what gives time its direction and gives you your sense of past and future. But why the beginning was so pristine, so finely ordered that it set the whole arrow in motion remains a genuine mystery, hidden in the very first moment of everything, quietly shaping every second of the life you are living right now, including this one as it slips gently into the next. Here is a mystery that is closer to home, quite literally, because it is about where our own galaxy is going. We tend to picture the Milky Way as sitting more or less still, turning slowly in place. But it is not still at all. Our entire galaxy, and the small cluster of neighboring galaxies it belongs to is rushing through space at a remarkable speed, hundreds of kilometers every second, all of us together streaming toward a particular region of the sky. And for a long time, no one could clearly see what we were falling toward. The pull comes from the direction of the southern constellations, and in the 1980s, a group of astronomers mapping the motions of many galaxies realized that a whole vast swath of the local universe, our galaxy included, seemed to be flowing toward some immense unseen concentration of mass in that direction. They gave it an evocative name, the Great Attractor, something out there. Some enormous gathering of galaxies and dark matter was gravitationally drawing us and everything around us toward it across the dark. And here is the frustrating, almost poetic difficulty. The Great Attractor lies in a part of the sky that is very hard for us to see because it sits almost directly behind the crowded, dusty central plane of our own Milky Way. Our galaxy's own body, its thick band of stars and gas and dust, blocks our view of exactly the region we most want to study, casting a kind of shadow across that part of the sky that astronomers call, rather beautifully, the zone of avoidance. So for years, the very thing pulling on us was partly hidden behind the glare and dust of our own home, glimpsed only indirectly through the motions it caused rather than by direct sight. With patient work using instruments that can peer through some of that obscuring dust, astronomers have gradually pieced together more of the picture and found that the Great Attractor is a genuine concentration of galaxies, and that beyond it lies something even larger, a truly colossal collection of galaxy clusters, drawing everything toward it from even farther away. Some now think our local motion is best understood as a slow slide along the great structures of the cosmos, down out of emptier regions and toward the richest concentrations of mass. But the full accounting of what pulls us and how much of it still hides behind the veil of our own galaxy is not entirely settled. Right now in the quiet, you and everyone you have ever known are being carried through space at hundreds of kilometers a second toward a great gathering of galaxies you cannot see, drawn by a gravity we can feel but not yet fully map. And you feel none of it. The motion is perfectly smooth, perfectly silent, the whole galaxy falling gently through the dark, carrying you along with it as you lie here, still and at peace. There is one more mystery worth resting with before we gather everything together, and it is the one that sits, perhaps closest to the question of why a universe like ours, full of structure and warmth and living things, should exist at all. It concerns the handful of numbers that set the character of everything, the fundamental constants of nature. When physicists write down the laws of the universe, the equations contain certain fixed numbers, quantities that the laws themselves do not explain, but that simply have the values they have. The strength of gravity, the strength of the force that binds atomic nuclei together, the masses of the basic particles, the strength of that mysterious dark energy pushing space apart. These numbers are, as far as we can tell, just given, woven into the fabric of reality, and our theories take them as inputs rather than explaining where they come from. And here is the quietly astonishing thing that many physicists have noticed. If several of these numbers were even slightly different, the universe would be an utterly barren place, incapable of forming stars or atoms or anything interesting at all. Consider a few examples gently. The force that holds atomic nuclei together is tuned just so. If it were a little weaker, complex atomic nuclei could not hold together, and there would be almost nothing in the universe but the very lightest elements. No carbon, no oxygen, none of the rich chemistry that makes stars and planets and living things possible. If it were a little stronger, the balance of nuclear reactions in the early universe and in stars would have gone very differently, again leaving a cosmos hostile to complexity. Or consider dark energy. If that gentle outward pressure had been much stronger than it is, it would have pushed the young universe apart so violently that matter could never have gathered into galaxies and stars at all, leaving nothing but a thin, ever-thinning mist, forever too smooth and too empty for anything to form. The value it actually has is extraordinarily small, small enough to let structure grow, and no one knows why it should be so finely poised. Again and again, across a range of these fundamental numbers, we find the same pattern. The universe seems to sit in a narrow band of possibilities that allow rich, complex structure to arise when the vast majority of imaginable values would yield only emptiness or chaos. This is often called the fine-tuning of the constants, and it is a genuine and much discussed puzzle. Why do the numbers governing our universe fall in just the range that permits galaxies, stars, chemistry, and eventually, minds able to notice any of it? There is no settled answer, and the possibilities are profound. Perhaps there is a deeper theory, not yet discovered, that will one day explain why the constants must have the values they do, showing that what looks like delicate tuning is in fact forced, inevitable, the only way a universe could be. Perhaps the numbers are, in some sense, a cosmic accident, and we simply happen to have drawn a rare and fortunate hand. Or perhaps, as some seriously propose, our universe is only one among a vast, perhaps endless, collection of universes, each with its own random set of constants, most of them barren and lifeless, and we naturally find ourselves in one of the rare ones where the numbers permit observers to exist for the simple reason that we could not have arisen anywhere else. Each of these ideas has thoughtful defenders and serious difficulties, and there is at present no way to know which, if any, is correct. The values of the constants sit there, precise and unexplained, quietly making a universe of structure possible, and the reason they are what they are remains one of the deepest open questions there is. We have traveled a long way tonight, from the invisible halos of dark matter wrapped around the galaxies, through the disagreement over how fast the universe is growing, past the survival of matter over antimatter, the flashes of radio light from distant skies, the cold spot and the strange alignments on the oldest light, the disputed dark flow, the vast unknowns of dark energy, the missing lithium, the walls at the beginning and inside the black holes, the silence where other voices might be, the slow fading at the end of all things, the fine-tuning of the constants, and the very arrow of time itself. And I want to gather all of it together now, gently, into a single quiet thought before we let go. Every one of these mysteries is a place where human understanding runs out, and it would be easy to find that discouraging, to feel small before so much that we do not know. But sit with it a moment longer, and something warmer emerges. Because each of these unanswered questions exists only because someone was curious enough to ask it, and careful enough to notice that the universe was not behaving as expected. Not one of these mysteries fell from the sky ready-made. Each one was uncovered, slowly, by patient people looking closely at the world. People like Vera Rubin, measuring the quiet turning of distant galaxies night after night, or Henrietta Leavitt cataloging the pulse of faraway stars, or the countless astronomers who built the telescopes and the satellites and spent their careers refining a single number. The mysteries are monuments to curiosity. They mark the exact edge of how far we have managed to see, and the fact that we can name them so precisely is itself a kind of triumph. And there is a lesson in these mysteries about how to hold not knowing, one that reaches well beyond astronomy. We live in a time that often treats uncertainty as a failure, that wants every question answered immediately and every doubt resolved. But the people who study the cosmos have made their peace with a different way of being. They live comfortably at the edge of the known, holding enormous questions open for decades, even for lifetimes without distress, treating each mystery not as a source of anxiety, but as an invitation, a place worth returning to, a door worth standing before. There is a deep and quiet maturity in that, the ability to say we do not know, and to find in those words not defeat but wonder. The universe does not owe us its answers on any particular schedule, and there is a real serenity in accepting that, in being content to hold a question gently and let it remain a question for as long as it needs to. Notice, too, that none of these mysteries diminishes the beauty of the cosmos. Quite the opposite. A universe fully explained, with every question closed and every drawer shut, would be a smaller and colder place than the one we actually inhabit. The real universe is more generous than that. It offers us just enough understanding to feel at home and just enough mystery to keep us reaching forever. The galaxies still turn, held by an invisible hand we cannot name. Space still stretches, driven by an energy we cannot explain. And that is not a flaw in the cosmos. It is, perhaps, the very thing that keeps it alive to us, keeps drawing each new generation to lie on their backs under the dark and wonder, exactly as their ancestors did, exactly as you might have as a child, exactly as you are doing in your way right now. And here is perhaps the gentlest truth of the whole night. Every one of these vast, distant mysteries is not really distant at all. They are all here in this room with you right now. Consider the dark matter. It is not only far away, wrapped around other galaxies. Its invisible halo fills our own galaxy too, and streams silently through everything, which means that as you lie here, countless particles of dark matter, whatever they are drifting through your body, through the bed, through the floor, through the whole earth, ceaselessly and without the faintest disturbance, an unseen wind of the unknown blowing softly through you this very moment, and you feel nothing at all. Consider the expansion of the universe. It is not happening only out there among the far galaxies. Space itself is stretching everywhere, in principle even in the space of this room. Though on such small scales the gentle bonds of gravity and matter hold everything firmly in place, so that you never feel the faintest pull. Still, the same swelling of space that carries the distant galaxies apart is a property of the very space your breath is moving through. And consider the ancient afterglow of the Big Bang, that oldest light we spoke of. It is not stored away in some distant archive. It is arriving right now from every direction, passing through your darkened room, faint microwaves that set out more than 13 billion years ago and are only now completing their journey by washing gently over you. You are, at this moment, being bathed in the light of creation itself, the oldest light there is, and it is as present in your room as the dark. Even the atoms you are made of carry the mysteries in them. The matter of your body exists at all only because of that ancient, unexplained victory of matter over antimatter in the first instant. The particular elements in your bones and blood were forged, partly in those first 3 minutes we could almost, but not quite, fully account for, and partly in the hearts of stars that lived and died long before the sun. You are not a spectator of these cosmic mysteries, watching them from a safe distance through a telescope. You are made of them. You are one of the places where the universe folded itself up into something that could look back out and wonder what it is. The dark matter drifting through you, the ancient light washing over you, the survived matter that composes you, the arrow of time carrying you gently from this moment to the next. All of it is not out there. It is you, and it is here, and it is now. So there is nothing to reach for tonight and nowhere to go. The whole cosmos, with all its beautiful unanswered questions, is already present in the quiet dark around you and in the warm weight of your own resting body. You do not have to understand any of it. It is holding you all the same, exactly as it always has, exactly as it holds every star and every galaxy, whether or not any of us ever learns its name. So let us begin to let it all settle, the way the dust settles in a quiet room after someone has finally stopped moving. We have gathered so many mysteries tonight, and there is no need to carry a single one of them with you into sleep. Let them drift back out to where they came from, out past the walls, out past the sky, back into the vast and patient dark that has held them for billions of years and will hold them for billions more. They do not need you to watch over them. They will keep until morning and long after every morning you will ever see. Think as your thoughts begin to slow of all the quiet people whose lifetimes of careful looking gave us these questions. Henrietta Leavitt, patiently measuring the pulse of distant stars by lamplight, never knowing she had handed us the ruler for the whole universe. Vera Rubin, night after night, watching the faint outer stars of galaxy after galaxy, refused to slow down. Fritz Zwicky, decades ahead of his time, insisting on a darkness no one else could yet see. Edwin Hubble and Georges Lemaitre, watching the galaxies drift apart and realizing the whole cosmos was growing. Paul Dirac, trusting an equation into a world of antimatter. Andrei Sakharov, wondering why anything survived at all. Stephen Hawking, showing that even black holes must one day fade. And the countless others, unnamed tonight, who built the telescopes and tended the satellites and gave their working lives to moving the edge of the known outward by the smallest, most patient degrees. They asked these questions so gently and left them so beautifully open that you and I can lie here tonight and simply rest inside them. And now feel where you are. Feel the surface beneath you, taking your full weight, holding you up as faithfully as gravity holds the stars in their slow orbits. Feel the warmth of your own body, this small, temporary, astonishing arrangement of matter that survived the first instant that was forged in ancient stars and that has somehow become something able to wonder about all of it. Feel your breath moving slowly in and slowly out, unhurried, each one a little quieter than the last. There is nowhere you need to be. There is nothing you need to solve. The largest questions in all of existence are content to remain unanswered tonight, and so you are free to be as unhurried as they are. Let your thoughts grow soft and shapeless now, the way the distant galaxies blur into a gentle glow when you stop straining to see them. If a mystery drifts back through your mind, the dark matter, the silent sky, the fading of the far future, let it pass through gently, like the ancient light passing through the room, touching nothing, disturbing nothing, simply moving on. You do not have to hold any of it. You only have to lie here and breathe and let the enormous quiet cosmos go on being exactly as it is, all around you and within you, keeping its secrets patiently cradling you in the dark. The galaxies are still turning slowly, held by a hand no one can see. Space is still stretching, gently carrying the distant lights ever farther apart. The oldest light in the universe is still washing over you, soft and cold and ancient, and none of it asks anything of you at all except, perhaps, to rest. So rest now. Let the questions keep. Let the universe hold them and hold you through the quiet hours ahead, and let yourself drift slowly, gently, out past the edge of thinking into sleep.